the only way I can.
All right, young scholars, today is our last lecture of the semester. If you've seen on Blackboard, we're going to be covering binary search trees, and we'll quickly go through AVL trees. So I wanted to touch on these as the last topic of the semester because in case you take Java 3, which is called data structures, you'll definitely see these concepts again. And as I told you last week, I've already opened the take-home exam for you. It just gives you extra time to do it. The due date is still December 4th, 11:59 p.m. So binary trees is a hierarchical structure. As you saw last week when we touched on them, they have a root, left subtree, and right subtree. Basically, just like a tree, except whereas a tree, starts out at the bottom, goes up, and then branches out. In Java programming, it's kind of from the viewpoint a little different. Basically, the exact opposite. The root is at the top instead of the bottom. So in essence, the root of the left, again, the opposite. Right subtree of a node is called a left right child. A node without children is called a leaf. So in this example, we have F, A is the child. However, if F did not have A as a child, it would just be a leaf. And the opposite is true for your right-left child of the node. So in this example, if 55 and 100 did not have any children, they would be considered leaves. However, they do have children. 55 has 45 and 57. 100 has 67 and 107. So technically, you could argue that 55 and 100 are children of the root being 60. If you wanted to search an element in a binary search tree, this would be the method or function you would utilize in order to do that. You would use Boolean search, and then for the element, Boolean because you're basically trying to find whether or not there's something there or not. So you would have to check if it's there, continue to go left. Oh, if there's nothing there, then we go right and we check everything on the right. But if we can't find what we're looking for, then we're going to return false. The element we're looking for is not in the tree, but if we find it, all right, the element's found. That 67 you were looking for, we found it here. This is primarily what we're going to do in class on Thursday with our programming examples. We're going to insert and delete elements from a binary tree. So if it's empty, you have to create your root, your initial part of the tree. Without that root, you can't add children, you can't add leaves, or anything. So here's an example. If root equals null, we create a new root. Otherwise, we use current root, and as long as the root is current, we continue to add new elements onto it. Additional children. All right, we're going to add one to the right. Oh, no, we already have it there. Okay, then we might want to, let's say we have the root of 60, and we already have a 60. So we have to add a different element, a different child. So 55, okay, that's a leaf. Oh, no, we're going to add a 45 and a 57 to it. Okay, now it's got children. We touched on a little of this last week. So there's the next 20 slides or so goes through literally what we're going to do programming wise in class on Thursday with adding and deleting a node from the tree. So I'm not going to talk through every one of these individually, but I'll just point out specifics as they come up. So in this example on slide 10, it states here we're inserting 101 into the following tree. And you look at this code and you're thinking to yourself, you know, how the heck does it know that we're adding 101? But what's in this code that's adding 101? As you go through the remainder of these slides, it's simply using 101 as an example to show you how we can change the root or add on to our leaves and trees. And it's checking that 101 against our root, our parent, our child, as it goes through these entire steps. Okay, we've gotten to the end of the tree. So now our current value is null. So then it falls down into the next method or function we're going to use, which checks 101 against that child, 107. So it would initially make it its own child. So then 107 would become a parent to 101. Since we have a new element we're inserting, we would return true, and 101 would be added on to the end of our tree. If you were to add 59 into the tree, it would go off onto the left, right side, because that would be the lower numbers. So 101, okay, it should be around 100 and 107. Makes sense, right? Whereas the 59, oh, okay, that should be around the 55 and 57. So in this example, which one is the parent and which one is the child? Anyone? No one? 57 would be the parent and 59 would be the child. Before we inserted 59, 57 would be a leaf. There's nothing coming off of it. So tree traversal, which is very similar to sorting that you guys saw previously, is the process of visiting each node in the tree exactly once. You could traverse a tree in order, pre-order, post-order, depth first, and breadth first. So the in order, you go to the left subtree, then go through all the nodes. Then you go through the right subtree and go through all the nodes. So it's literally, okay, one by one, in order. The post-order traversal is to visit the left subtree of the current node first, then the right subtree of the current node, and finally the current node itself. So it kind of bounces back and forth between the different subtrees. Whereas in order, okay, we do everything in an order. Okay, then we go on the other side and do all of that in an order. The pre-order is obviously the opposite of the post-order. You go to the current node first and then backtrack. Okay, I'm on the left-hand side at the bottom. I go back to the root. Okay, and then I go down on the right-hand side. Then the breadth first is to visit the nodes level by level. So let's see if I can draw here. If you had your tree, you got a level here, a level here, and a level here of nodes. The breadth first would start at the root, then go through all of your nodes on this first line, then all of the nodes on the next line, then all of the nodes on the other line. So the breadth first traversal is kind of the most uncommon because it's going to take you forever to get to whatever your current node is there at the end. Whereas in the pre-order, you're already at the current node. So if you wanted to add, you might start with a pre-order traverse. All right, where's our current node? Let's get there. All right, we're there. Okay, now we can add on as we need to. So within Java, there is the tree interface where we can search, which allows us to return a Boolean option, true or false. Hey, is it there or not? Tell us, true or false. We can insert or delete. And then ask whether or not that element was in fact inserted or deleted with that Boolean. Hey, did we insert 57? Goes and searches through that tree. Yep, 57's there. True. All right, did we delete 48? Nope, 48's still there. False. Then as you just saw, we have in order, pre-order, and post-order, which will print those nodes similar to as we've seen with a sort. So pre-order will start at whatever the current node is, print that out first, and then the rest of the tree. Post-order would be the opposite. And in order would start at your root, print out everything on the left, then print out everything on the right. The get size function will return the number of elements or nodes within the tree. The isEmpty function will allow us to find out if there's anything in the tree or not. Do we need to create a new root? If it's empty, you'll see a true value returned. So you know you now have to create a new root and add to your tree. And then lastly would be the clear function, which was delete everything in your tree. All right, I don't like the way that tree looks. Like think of it when you're putting your Christmas tree up, maybe. I don't like the ornaments here. I'm going to move them around. Similar idea with the clear. I'm going to get rid of everything in the tree and start over. Then there is the binary tree class, often referred to as BST, which extends the abstract tree class. So you would start with your tree node, your root. You would add it in. You would decide on what your size is. I'm going to have 12 nodes in my tree. Then you would use the BST function to create your new binary search tree. Then you would do objects, whatever your element is, and then your brackets in order to add an array of elements. Your nodes, you'd put those integers, your numbers there. And you could also do path E with your element as well, which is going to return the path of nodes from the root leading to the node for the specified element. It's very possible that the element may not even be in the tree. You may say, oh, okay, go to 49, and there's no 49 in the tree. So if you were to insert all of these names or strings into a tree, George, Adam, Michael, Daniel, Jones, Tom, Peter. George is our root. Then we have Adam and Michael as parents. Daniel is a child of Adam. Jones and Tom are a child of Michael. And Peter is a child of Tom. So technically here, Tom is a child to Michael, but also a parent to Peter. So you'll notice here in the pre-order that it has George first. So what does that tell you based on what I've just explained? George is the root, but is also what in this situation? It should give it away when you look at post order that George is last. So in this example, George is not only the root, but the current node that we're on. So pre-order starts at whatever your current node is. So George is the current node. Post order goes to the current node last. It starts in reverse of pre-order. Whereas in order, all right, we're at the root. We start at the next one on the left. Okay. Adam, Daniel. Okay. All right. We were already at the root, but let's go back to the root because we have to start on the other side now. So it would be Adam, Daniel, go back to George, then to Michael, then to Peter. Oh, well, we skipped. We have to go back. So then it goes back to Tom. Whereas with a example, as you saw with the other one, that row would be looked at first, then the next row, then the next row for those specific examples of the breadth first traverse. So the point of knowing what your current node is, where you're looking, is because if you want to delete something, if you don't want to delete that current node, you need to know, okay, we're on node 57. We're on node George. Okay, no, we don't want to get rid of that one. let's move our current to a next node. So you first need to locate the node that contains what you want to delete, as well as its parent. So let that current point to the node that contains the binary tree element that you're looking for, and parent point to the parent of that current node, so that the current node may be a left child or a right child of that parent node. So you have to consider those two different options, left or right. So in case one, the first possibility, the current node doesn't have a left child, like you see in the first picture here, no left child. So you simply connect the parent with the right child of the current node, the subtree. So if there's no left child, oh, okay, we're just connecting with the right child. You don't necessarily need to have that little tree split, if you will. So if you wanted to delete node 10 in this example, you'd in essence be bumping 16 out as well. See how 16 now falls all the way further down, even though technically it's still on the same row? You now no longer have a left and right parent to your root node. And again, with the breadth first, you'd take 40 in one, 16, 30, and 80 in one, 27 and 50 in one. If 20 was our current, our pre-order would start there. Our post-order would start, let's say, either 27 or 50. So in the opposite case, if there's a left child, you're going to have rightmost point to the node that contains the largest element. And then check parent of rightmost against that rightmost. The rightmost, though, cannot have a right child, but may have a left child. So you might want to replace the element value in the current node with the one in the rightmost node. Then connect it with its parent with the left side. And then you would delete whatever that specific node is. So here's an example of how that would work. Okay, our left is there. We want to get rid of it. We drag it down. All right, now it's a parent. Now we can add children onto it if we so choose. Okay, we have the parent here. We have a child. Then that child also has a child. Yep, no, we don't want that in the middle. We get rid of that. So now we have that parent only has that one child. That intermediate is now gone and deleted. So this is why I'm kind of, this is the last lecture related to these, because it's more or less fairly complicated. And this is especially one where on Thursday, when you actually see the code, you'll be like, oh, okay, this makes a lot more sense now. So again, here would be an example of that. In this example, we're going to try and delete the number 20. So you see here that 20 is our root. So by deleting our root, everything on the left, right is now examined. What's the next biggest number? Okay, our 16 is, it now becomes our root. So 10 drops as 16's child. And then 14 becomes 10's child, as you see in this example here. So it always pivots off to the left, right. The left-hand side, if you're looking at it like this, if you're looking at it as an actual tree, that would be the right-hand side of your tree. That's why they refer to it as the left-right node. So again, it's fairly complex, but once we go through the code on Thursday, it'll look, hopefully, a little easier than it sounds. So as you've seen, this is kind of complex. So in order to search for all these different trees, oh, do we have a 47 in the tree? Oh, do we have a Bob in the tree? It might take quite a bit of time to search for that. That is why individuals use those traverse options. All right, just print out everything in the tree for me. So this way I know what's there. This way, once that basically sort is printed out, you're now able to see everything that's there. Now, we've covered iterators multiple times in multiple ways throughout this class, but as a reminder, it's an object that provides a uniform way for, in this instance, with trees, traversing the elements in a container such as a set, list, binary tree, etc. So related to that, for trees, you could use the hasNext function, which is going to return true if the iterator has more elements. Let's say you only look through 8 elements and there's 12 in the tree. That hasNext is going to return a true. As long as there's at least one more element that you haven't looked at yet, it's going to return true. The next function will allow you to return the next element in the iterator. Oh, do we have a 5? Do we have an 8? Whatever your next node is, it will now spit it out for you, return it. Or say you don't want that number. It was no good. You could use the remove function. Okay, we don't want that 5 node. We didn't like that. You can remove it from the iterator. And like I said, this all sound so complicated. And when you go through it, when we go through it together with the programming code on Thursday, it'll seem so much easier than it does today. But like I said, I wanted to touch on it because if you take data structures, this is definitely something you're going to see related to it. And then next, we're going to cover the more advanced ones, the AVL trees. So within an AVL tree, or the reason why we tend to use them, is that the search, insertion, and deletion time for a binary tree is dependent on how big that tree is. Whereas an AVL tree, it's more balanced. So they were invented by 2 different individuals, if you feel like knowing that. So it basically cuts the difference. Okay, the left is 45%, the right is 55%. And it cuts down some of the compiling time, computing time, however you want to describe it, to provide the information that you need to get it to you in a quicker fashion, so to speak. So it basically checks, okay, are there more nodes on the left-hand side or the right-hand side? If there's more nodes on the right-hand side, we're going to go through that first and do that. Or it could rebalance or rotate the nodes to make each side of the tree balanced. I'm sure you've seen in real life, if there's thicker branches on one side of a tree, it tends to lean over to that side. So here's some examples of how that works. So you have left or LL imbalance and LL or left rotation. So you see here the left-hand side, we have this giant child, a smaller child, and off to the side, the root only has that leaf there. When we adjust it left, okay, that giant leaf stays connected to B, A is bounced over, and A now takes over the two smaller nodes. This balances out the tree. Now, obviously, you can't do this in real life with a real tree, but you can within Java programming. If you have one giant, real thick branch, you can't, move the other branches two at a time to the other side to balance it out. However, like I said, in Java programming, you can. Then the opposite is RR, or right rotation. In this example, it's the same as the left. All right, there's one bigger one. Let's switch everything around so everything is even. Now we do the opposite with the right, okay? This one's much bigger. Let's bump B up, drop A down, so A has the two children underneath it that are equal or level with that other node. But then it gets a little more complicated when you have LR, or left-right rotation. So in this example, okay. On the left-hand side, we have one node that's much farther down, another node that's much farther down. On the right-hand side, we have a node that's way up there. It's even with our other parent. So with left-right, all right, let's put T1 and T2 on the same level. So T2 is now no longer a child of C. It's now on B. C gets bumped up all the way to the root. A gets bumped down. And T3 and T4 are now children of A. And T1, T2, T3, and T4 are all on the same level. So here C becomes 0, okay? -1, 0, okay. We have our children below them. And with left-right, we start by looking at the left and then considering what is on the right. Whereas the opposite, right-left rotation, we start by looking at the right. All right. T4, we can fix that up. All right, let's drop T4 down. If we drop T4 down, we have to drop T1 down. Okay? But if we do that, we then have to drop A. But C is a higher number than A, so we have to bump that up. C is now the root. Everything else drops down except for B, which takes T3 on as its child. So again, like I said, this is fairly complicated, but once you start seeing the code and see the actual Java code associated with these, you'll get a clear understanding on Thursday when we touch on this. And just like the others, there are specific functions associated with these. So you can create an AVL tree using that AVL tree function. You can add objects to it, string, integer, what have you. You can create a new node. You can see, okay, did we properly insert this new node? Oh, did we properly delete this new node? True or false? You could also even change the height. You could do what I just demonstrated, balance path, okay? Do we want more on the left or right? Doesn't matter. Oh, okay, it matters. All right, let's balance the entire tree. You can check what the balance is for that tree using the balance factor function. And then for each of them, you can utilize what we just demonstrated. You would, instead of, balancing overall, you could say, all right, balance left, left. And it'll make those adjustments we touched on in slide 8 here. Whereas, okay, we check, all right, left is unbalanced, move that up. Or you could check left, right, which was slide 10. All right, we look at the left first, then we look at the right, and then we make our decision on what to do. Or you could balance right, right. All right, we start by looking at what is here on the right, and we make adjustments to balance everything else out accordingly. Or lastly, you could do right, left, like we saw here on slide 11. All right, we start by looking at what's on the right, then we look at what we have there on the left, and we make our decision on how to properly balance the tree accordingly. All right, so as always, I'm going to post up the recording of our lecture today. Once it's downloaded from Zoom and uploaded onto YouTube, the link for you. As a reminder, no more homework assignments. All that there is left in the course is this take-home exam and your presentation for your project. So on Thursday, we're going to meet. I think I have 4 programs set up, but I may just upload the 2 easy ones, and then we'll go through the 2 more difficult ones together so you get a clear understanding of what we just talked about. Because like I said, it's kind of difficult to grasp, so to speak. And that's why some of these YouTube links for other people discussing this are quite lengthy if you've looked at them. So I want to also point out, though, next Tuesday, there's no class. I gave you the whole week off because next Thursday is Thanksgiving. So after Thursday, when we go through some programming exercises on trees, all you guys have left is that take-home exam, those 3 questions I showed you last week, and putting together your hangman game or tic-tac-toe game. Like I said, that following week after Thanksgiving, the 28th and the 30th, I'll have Zoom set up for you to pop in and ask questions as you need to. But otherwise, if you don't have any questions, just, meet with your other group members, make sure everything's done, your program compiles and runs, and that you're practicing your presentation to give on the 5th. All 3 groups should be easily able to go and do their 20 minutes that day. And like I said, if it's needed, that Thursday, the 7th, I'll have some kind of extra credit exercise available for those who need it. So let's see here. We have the group Zaza and Franny. Hopefully you guys have connected and spoken about what you're going to do. Amelia and Grace, hopefully as well. And Lana, Al, and Calvin are the last group. So if you have any specific questions on what's next, feel free to ask them. I'm going to pull up the group project requirements just so you see them again. So again, 25 out of the 40 points is, okay, our program works. We did what we need to. And we have comments that basically say, okay, Amelia did this half, Grace did this half. Or in the case of the group with 3, all right, I did this third. They did, this third. The other person did this third. And then the 15 points otherwise is for that 20-minute presentation. And I'll post up probably sometime next week in this 1128 and 1130 folders some suggestions on how you can go about effectively presenting, avoid and just take a pause if you need to, etc. So are there any questions on that? No? Okay. So I will point out when you submit your group project, I don't care if you use a PowerPoint slide deck or not for your presentation. When you're submitting that, you want to submit your code, your hangman game code or your tic-tac-toe game code. All right. So if there are no questions, I will see everybody on Thursday for our last programming session. Enjoy the rest of your day. Hopefully while it's still sunny out. Take care.